The Mimics Innovation Suite can help you with your morphometric analysis. I'll be showing you some workflows within the software that will help you analyze 3D anatomical models. Morphometric analysis allows for the study of variations in anatomy. This becomes especially important in studying groups or populations. For example, analysis of the pelvis bone for a group of patients with hip dysplasia may uncover certain important patterns within the alignment of the pelvis. Similarly, analyzing the femur bone for an Asian population may uncover crucial differences in shape that would not allow for a standard implant that fits for a Caucasian population to fit for the Asian population. Our white paper on our ATOM services discusses this in more detail. Though our ATOM services takes morphometric analysis to the next level by statistically studying shape changes of the total geometry, the Mimics Innovation Suite still offers many other opportunities to analyze anatomical data by taking measurements on the geometry. In this tips and tricks, I'm going to go over how to perform some analysis on the femur. Specifically, I'll first look at how to determine the mechanical axis of the femur, then measure the femur neck angle, move on to get the isthmus point of the femur, which is finding the narrowest point on the femur shaft, and then finally use the previous information to measure the version angle of the femur neck relative to the epicondyles. Then for the pelvis, I'm going to show you how to measure the inclination angle of the acetabulum relative to the anterior pelvic plane. Now keep in mind that these measurements shown are only a sample of the measurements possible, so if you have certain measurements that you are interested to perform, we urge you to reach out to us and discuss potential workflows within the software. So the first measure that I'm going to show you how to obtain is to get the mechanical axis. The mechanical axis moves from the center of the proximal joint to the center of the distal joint, so from the femur head to the condylar center. And in order to get it, we have to obtain a sphere to represent the femur head and identify two of the epicondyle points to determine the center of the condyle. So let's first start by getting the center of the femur head. First of all, you'll notice that the model of the bone is a solid model, so there's no internal geometry. If you're not familiar with how to obtain a model like this, you can always discuss with us and we can show you workflows for segmenting a complete geometry and getting it solid like that without any internal detail. In order to get a sphere that represents the head of the femur, we can create a sphere and fit that sphere to the femur head. So what we first have to do is to mark the portion of the femur head that's circular. And essentially what we'll do is Trimatic will fit a sphere to this surface that we've identified. And you can see the marked triangles are selected here as the fitting entities, and there we have a sphere that fits onto the head. Keep in mind that how you identify this surface is very important. You don't want to accidentally identify areas that are not circular and don't represent the circular shape of the femur head. So you shouldn't select the neck. You should really stop on the portion of the head. You can unmark all the triangles to put you back to your previous. And now if I hide the femur, you'll see that we have a sphere that represents that head. So the center of this sphere will be the center of the proximal joint or the femur head. Then we need this center of the condylar joint as well. In order to get that, there are a few different definitions in the literature. Some people discuss using spheres to fit to the posterior portion of the condyle joints, and then using those centers as your landmarks. However, what we will show you here is just marking the epicondyles. You can see it as a landmark on the femur, and using that you can mark. Keep in mind that if you're comfortable using mimics, you can also do these on the medical images in mimics and bring it into thematic. So over here you can see this joint. There's an anatomical feature over here, and we're going to mark it on the center of that anatomical feature. So now I've marked both of my epicondyle points, and what I would like to do is obtain the center between these 2 points. Since you can't do that with a create point tool, the workaround is to create it with the datum plane. So I'm going to fit a datum plane between these 2 points. And the origin of that datum plane is my center point halfway between those 2 points. So I'm going to hide the datum plane and use that origin to create my mechanical axes. And all I have to do is use the origin of the datum plane and the origin of the femur head sphere that we created. And now we have a mechanical axis. Next, I'll show you how to obtain the neck angle of the femur. In order to obtain that, we'll use the previous sphere that fits the condyle, and that will designate the center of the neckline. And then we'll also create an arc that fits around the femur neck, and that will give us a second point in order to draw a line that represents the angle of the neck. Then in order to get its angle, we will do that relative to the femur shaft, and we'll fit a cylinder to the shaft in order to be able to measure that angle. So we already have the sphere that fits the femur head. In order to draw the femur neck angle, we can create a curve. And the goal is to draw it on the narrowest point of the femur, on the femur neck. It's a little bit subjective, of course, but that's whenever you're working with anatomy, there are some areas where things have to be a little bit subjective. Now that I have a curve, I can fit a circle onto it. And the center of that circle can represent the center of the neck. But what I finally need is a line that represents the femur neck, and I can draw that line between the center of these 2 objects. Now that I have a neckline, I can make a measurement if I have a reference to measure it against, and I'm going to use the femur shaft as that reference. And of course, as we're doing this, keep in mind there can be other definitions of how you would like to define the neck angle. If you want to explore how your definition can be translated into a workflow in the software, feel free to reach out to us. Over here I mark the shaft, and now I can fit a cylinder to represent the femur shaft. And with these two, the femur shaft and the neck line, I can go ahead and make a measurement of the femur neck angle. So I'm measuring the angle. With the line-to-line method, using the axis of the shaft and the femur neck. The third measurement that I would like to obtain is the isthmus point of the femur, which is the narrowest point on the femur shaft. Basically, we would like to measure the best fit diameter of the shaft and determine where's the narrowest. In order to do that, we're going to go to Mimics, switch back to Mimics and do it there. The centerline tool was heavily improved in Mimics. So if you create a center line, you just have to select the femur and fit a center line to it. You can use the features of the center line to determine the narrowest point. So here we fit a center line. It includes the curvature of the neck. What I would like to do is delete that curved portion and then analyze the narrowest point on this center line. So the center line is stored under CAD objects. I can access it there. And if I right click, I'd be able to delete a certain portion of the center line. So I'm going to hide the femur and go ahead and do that. Now I have just the shaft portion of the femur. Now with the center line, you're able to make various measurements, such as the best fit diameter at various points of the femur. However, what I have to do is keep making measurements on different portions of the center line. Naturally, that's going to be tedious, but what we can do is, to find out the narrowest point, is actually export the best fit diameter to a text file. If you go to the properties of the center line, you'd be able to select that particular branch of the center line that represents the femur shaft and export the best fit diameter to a text file. Then what I can do is use Excel to import those parameters, and essentially I'll be getting the best fit diameter at intervals of that center line. So in order to do that, I can go to the data section, import from text, and select the file that I exported from Mimics. What I need to do is separate the values into different sheets, so I can select delimited and just select all the delimiters here. And now I have a list of the best fit diameters, including the location and the direction of the circle that fits that. So what I need to do is filter through this list and I can find the smallest best fit diameter, and that would be my isthmus point. So then if I copy and paste the XYZ coordinates of the center of this circle and also the direction XYZ of that circle, I can create this circle in Thematic that represents the isthmus point. Or of course, if you just need the values, you can take it from the Excel file and record that as part of your measurement. Now I'll show you how to measure the version of the femur neck relative to the condyle. So it's going to use a few measurements and landmarks from the previous. We're going to need the mechanical axis so that we would be able to make this measurement in the direction of the mechanical axis. So we're going to create a plane orthogonal to the mechanical axis and ensure that the measurement is made in that direction. Plus, we're going to use the condyle as a reference. So in this case, I'm going to use the epicondyles and create an epicondylar axis as my reference to measure version. Oftentimes in the literature, you'll also see the posterior condyle points used, or other definitions that are used as a reference to determine version angle. So let's first start by using the mechanical axes and creating a reference plane. So I can create a datum plane that's normal, orthogonal to the axes. Simply have to select the mechanical axes in the correct direction. And create a plane that's orthogonal. Then I'm going to use the epicondylar points to create a reference line. I already have the neckline available. I'm just going to hide the other measurements to put them out of the way. And now what I would like to do is measure the angle in this reference plane. Okay, so it's the projection of these two lines on that plane. I'll be measuring that angle. And I can do that quite easily using the angle measurements. So I'm measuring the angle between a line to line, but I'm defining a coordinate system by which I would like to make that measurement, which is going to be the plane. And of course, I'm going to project on the xy of that plane. So now I can just select the line, the two lines that I want to make a measurement for, and I'm able to make a measurement. One thing that's frustrating is the way I've made the measurement. You could see it's not very conducive to taking a snapshot. In order to gain more control and make a smaller measurement, I'm going to undo and show you what you can do. If I move the neckline closer to the reference line, then I would be able to control the measurement better. And I can do that quite easily with the translate function. I'm going to move the neckline, a point-to-point movement, so I'm not changing it, I'm not rotating in any way, I'm just transforming it to another location. And I'm going to move it from its current origin to the starting point of the reference line. And I'll create a copy. Okay, so now I can do the measurement with more control. By using the relocated line. Okay. So there we go. I've made a measurement of the version of the neck. Right? And it's been projected according to the axes orthogonal to the mechanical axes. Next I will show you how to measure the hip inclination angle. I've shown how to measure it in 3D space. Of course, you can use the same technique used for the version angle in the femur exercise to measure this angle in a specific reference plane. Currently, what we've done is measured it as a 3D measurement in reference to the anterior pelvic plane. So the anterior pelvic plane is shown over here. You can see that the measurement is in reference to that plane. And in order to do that, we create a plane to represent the acetabular cup. So I'm going to show you how to create both these planes and then finally measure the inclination angle of the acetabulum. So the first step would be to get the anterior pelvic plane. A very simple method could be to do it visually for those who are not overly concerned about having a precision on how the anterior pelvic plane is defined. Generally, you can define it on the ASIS, so the ASIS over here. On the right and the left, and then use a third point over here. Again, you can create it by creating a datum plane and selecting those 3 locations. However, if you would like to have more accuracy, this would just be your starting point. From here, I would use this plane in order to define the direction of an extrema analysis. And with the extrema analysis on the pelvis in the direction orthogonal to the plane, so the z-axis, I would go ahead and preview the extreme locations on this pelvis. Okay, so I'm previewing it in the wrong direction. I'm just going to flip. Right now we're previewing it to the back of the plane. I'm going to flip that so we're looking at the front. Okay, and in this way I can find the most extreme points in the direction of that plane to define my 4 points of interest. So I'm going to create these 4 points and label them. First I have the ASIS there. the ACES on the left as well, and then the 2 points on the pubic area. If the extrema analysis is showing 2 points close to each other, that's because they have the same extreme, so they're the same distance on that platform, and that's why it's representing 2. Now when you create a datum plane, you can only, if I use the 3-point method, I can only create 3 points. So what I'm going to do is create an average, or the midpoint of these 2 points, as we did with the epicondyles in the femur exercise. I can create a datum plane between them. And the origin of that datum plane will give me my 3rd point of interest. So now I can create a more accurate datum plane using the ACES right, ACES left, and the origin of this datum plane, all defined by the extrema analysis. And that could be my anterior pelvic plane. So now I have my reference plane, and I would need to go on to create a plane that represents the rim of the acetabulum. In order to do that, I would mark the rim of the acetabulum. So I can use the mark, brush mark, and wave brush mark. Set the selector to a rather small selection, so I can focus in on the rim, and just browse across to select the rim. You don't have to make the selection in one continuous go, so you can do it in parts. And you can always use the control option to deselect some parts if need be. So in this area I would avoid, depending on your definition of how you define the acetabulum rim, but you could avoid this last dip where it merges in with the other portion of the pelvis. Once you've marked the triangles, you can fit a datum plane to the marked triangles, and that would place a datum plane to fit the surface that you've marked. So to essentially find the average of those marked triangles. Now that plane represents my acetabular rim. With these 2 planes, I can go ahead and make a measurement between them. Can determine where I would like to place that measurement. And that way you can measure the inclination angle.